About 20 years ago, 25 years ago, we discovered in the premotor cortex of the monkey a specific set of neurons which fire both when the monkey performs a motor act and when the monkey observes a similar motor act performed by the experimenter or another monkey. In these 20 years, this mechanism, the mirror mechanism, has been discovered in many species. First in bird, then in rats, then in marmoset, recently also in bat. It's very interesting because in bat they are the mirror neurons related to space, so you recognize the position of another animal because it's similar to your previous position. Anyway, today I am going to speak essentially about human story because the time is limited. But before that, I would like to show a film which is taken from the monkey, which gives you immediately the scaffold for what I have to say. So here is the monkey brain, and you see some areas. We recorded from area F5. And now I will show you a mirror neuron recorded from this area. What you have to do is correlate the sound, tac, 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 that you will hear, which are the action potential sent to a loudspeaker, with the action of the monkey or of the human being. This is a grasping neuron.
Fanno un altro così. Come prima. Ancora.
The mirror effect is the same action potential, the same neuron.
Fai ancora.
It's a kind of dialogue. Well, what is clear, I think, from this movie? First, that it's highly repeatable. Second, that's immediately evident. We don't need very sophisticated statistical analysis to demonstrate that these neurons exist. They are there, you can see them. The third point, which is very important, that you don't need exactly the same motor act that it's encoded by this neuron, but the goal should be similar. That's very important because sometimes people say, we have mirror-like neuron because it's not exactly the same action. Also here it's not the same action. Typically, the action have the same goal, but it's not identical. We have a very minority, at least in monkey, of neuron which is exactly the same stuff. Well, what this means? We have a transformation of sensory information into motor information. That's what you saw. This transformation, of course, does not occur only in this area, but here you see a circuit in which you see that visual information arrives from the external world, and then in the parietal lobe, it starts the transformation where mirror neuron appear, the transformation in area AIP and in PFG. Then it goes to F5, and finally it arrives also to primary motor cortex. The data of Roger Lemon in London demonstrate there is a set of corticospinal neurons which fire when they see an action. There is an interesting aspect in these neurons, or in this set of neurons, that some of them are inhibited when they see an action. They are excited when the monkey do, and are inhibited in the other case. So to summarize what we have that the model, my model of grasping, it's elicited when I see another person doing the same thing. So why we need this model? On this point, I think Marc Generot was the person who made the most interesting speculation. So the reason is that if I have the model, I understand much better what the other people are doing. The best example are taken from sport. If you never played cricket, you will never understood why it's good some action that player is doing. I play tennis, I can understand that Federer is really very, very good because some positions are very difficult, you know that. And another example are the dancing. There's a nice experiment done in University College by Calvo Merino, which showed that you've never danced. When you see somebody dancing, you have a very little activation of mirror neurons. But if you are expert dancer, you have a very strong activation. There is plenty of evidence, especially from sport, that demonstrate that if you know it, your mirror system is much better, is much stronger activated, and also the people explain much better what they see. Well, but I said I want to speak about human. The mirror neuron in humans has been demonstrated in several ways by using, for example, EEG, by using MEG, but most experiments were based off fMRI. The first experiment we did in Milano with Fazio and Massimo Matelli from my lab, and we found that there was activation of the premotor cortex and the parietal lobe in humans. Subsequently, we repeated this experiment with Scott Grafton, still PET experiment in Los Angeles with small variation, and it was very clear that the motor system in humans became active when a human person observed another individual doing an action. But most experiments were done with fMRI, not PET. The first experiment were PET experiment. Here it's a review article written by the group of Carl Silles, and Carl gave us this picture that we slightly modified, Avanzini modified it. But you see that's a review of 90 cases, and you see how the brain is activated when you observe action made by another person. Here there are action also made with mouth and with proximal, so it's a bit larger than what I showed you before. But you see this. There is a great similarity between monkey and humans, showing that in evolution, this capacity to understand action of others started early. Also, marmoset has already this, but then in humans became richer. Humans also use tools. So with Guy Urban, we did an experiment to see what happens when you show action made by hand, or in the original experiment, by a robotic arm. In A is a human hand grasping an object. In the B panel, it's a robot arm. The kinematic is completely different. The shape is different. So essentially, it's very similar. If you look at the lateral view of the brain, it's very, very similar. If you do, however, a subtraction, you have in human, when you see a human action, an activation of inferior parietal lobe on the left side. That's the area the region of which determine apraxia, and you know that apraxic patients have a strong difficulty in using tools. With Urban, we also repeated this experiment with many other tools. It is also left hemisphere, left parietal lobe, which is active. So we understand the action of grasping using a basic mechanism, which is present also in the monkeys, but the specific tool use, it's a human new evolution. Now, one obvious question is the following: which are the actions which we understand using the mirror system? So we did with Buccino an experiment in which we present, that's an fMRI experiment. So imagine the student, it's lying in the scanner, and we present first actions which are common to different species. So you see here a human being biting, a monkey biting, and a dog biting. So all of them do the same thing. Then in the second part of the experiment, we show it actions which are species-specific. So humans saw lip reading, so they saw a film in which somebody was reading, there was no sound. For monkey, we use the so-called lip smacking. It's an affiliative gesture that the animal uses in order to say, we are friends, please don't attack me, and so on. And the dog was barking, again, without sound, no sound. Well, the results are here. biting. If you look at the left hemisphere, the praxic hemisphere, there is no difference. If I do a subtraction, it will be 0. So when we see a dog which is biting or a monkey biting, we still put on ourselves. It's our model which is activated. We understand it as if a human being was. The things change radically here. For speech, or lip reading in this case, there is activation of Broca's area and also something in the posterior area, maybe Wernicke, maybe something similar. But look at the third panel, dog. For the dog, we have an activation only of the visual area. So we don't understand dog barking using our model. We don't know what means barking. I can say bow, 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 bow. Any language has a specific way to see. But to repeat how the dog bark. Anyway, we don't have. Incidentally, here it's interesting. I received a letter from Sperber, which is a French philosopher, who said, I asked my son, would you like to be a dog? Do you like dogs? He said, no, I don't want to be a dog. Why? Because I don't know how to move my tail. So it's a very deep answer, because it's a completely different set of action, which we don't know how to do it. So, but the point is, with Corrado Siligalia, we offer this explanation, that we have two radically different ways to understand action of other. One is from the inside. I understand you because I see what you're doing in my motor system. Then I can also understand by inferential, by thinking, like I understand physical law, why an apple is going down, why an airplane is flying, and so on. So they are completely different two ways. And you see, that's very important also for emotion, I think. I will briefly tell you something about vitality forms. Vitality forms is something which is absolutely neglected by neuroscience, and yet it's something extremely important in social life. The term has been coined by Daniel Stern. Daniel Stern was a great psychiatrist and psychoanalyst. I don't show you this very complicated definition that he gave, but I give you an example, and you will see why vitality form is so important. Look at these two people. Be quiet. Be quiet. So it's the same action. The goal is the same, the meaning is the same, but the way in which it's executed, the form is completely different. Here it's even better. A gentle, not really gentle. I am afraid this couple has not a long survival time. Anyway, Daniel Stern described that, but neuroscientists somehow ignored it. So we studied with Di Cesare, first with Daniel himself, and we, in fMRI experiment, we contrasted what happens in the brain when you have to decide the goal of an action, when you have to decide the vitality form of the action. Vigorous, kind, and so on. The other experiment that I want to show you have three moments. In one, the person in the scanner observes an action on the left. In the center, he thinks the same action, thinks that he's doing. It's the motor imagery à la Jeanneret. He thinks that he is doing the action, and he can think in a gentle way or in a rude way. The third is execution. Execution was very difficult to do in fMRI, so it was a very small movement, but the instruction was to do in a gentle way or in a rude way. Anyway, the result was very clear. If you look at the center panel, you see motor imagery. And it's the cleanest because you have no vision, you have no motor, and you see. Remember that that's a transparent view. So you see in all of them, maybe I can show you with the arrow, this area here, which is the anterior insula that you see from the brain. But look at the insula, really. you can see that in all cases, when you have a motor imagery of an action, kind or rude, you have an activation of the central insula, the same when you observe this action, and also during the execution. So again, we have a mirror mechanism, we have a model of an action which can be rude or... we made several experiments, he did especially, but one question, which of course is the following: how is possible that insula modified the circuits which determine that your gesture is kind or no? So we look at our data, that's the work essentially of Marzio Gerbella. He looked at our data in the monkey and saw and examined the connection between the central part of the insula, and there is a very strong connection with the circuit which determine the modification of your movement. So we have a circuit which makes the action, but according to my internal state, Stern was very careful to say this nothing to do with emotion. That's an internal state. You can call it mood, but it's nothing to do with classical emotion. Well, when you are in good mood, you do in a gentle way, otherwise, and that's modified because insula send information to the center. Now, I mentioned the insula, and now I can move to emotion. We studied, in particular, insula for several reasons. One, because I think it's a very interesting structure. Second, because I think never, in no structure of the brain, for no structure of the brain, has been said so many stupid things. Even the soul is in the insula. Everything is the insula, especially the rostral part of the insula is a kind of miraculous thing. Well, insula is much simpler than that, but in order to say that, we have to stimulate it. And this is an experiment which was done essentially by Fausto Caruana and Gezzini. It's stimulation of the insula, using the long period of stimulation, like Michael Graziano and Charlie Gross did in Princeton. Well, here is different sector of the insula which completely different function. But what I am interested now is only anterior part of the insula, which is red and blue. The green we have not understood what is going on. It was very ambiguous, but the other two was very clear, and I will show two movies. In this case, there is no action potential, but you have look at the behavior of the monkey, and will be a red light. The red light indicates that we stimulated the animal. Red light. Red light. Well, I think it's very clear that every time appears the red light, the monkey starts ingestive movement, move the lips, move the tongues, and so on. Well, now the electrodes is moved ventrally. Now it's not in the red, but the blue area, ventrally. And now look at the behavior of the monkey. Again, same convention as before. Red light. Well, I'm sorry. Should go. Yes. Red light. Obviously, it's not happy. Look at something which typically it's very good. Very surprised. Good food, disgusting. Really very surprising experience. Now there is no light. She's eating it. We reinforce her in order to keep her quiet. Red light. You see, it's incredible, the surprise of the monkey, something which was very good 1 second before, now it's incredibly disgusting. Well, what it means, that in the rostral part of the insula, Anterior Insula, we have two zones. Both of them are for ingestive, but one is positive ingestion, and one is for negative ingestion, or disgust. So it's, the next step would be the Broca's area, language, and so on. Anyway, that's discussed in animals, in the monkey, with, well, in the lab of Bruno Vicaire in Marseille, we made some experiment on disgust with Vittorio Gallese and Christian Kaiser. Why Marseille? Because in Marseille there is a group of people which are very good in manipulating odorants. So they gave odorants to subject, and the odorants could be pleasant, unpleasant, or neutral. The second part of the experiment, again, was two parts of the experiment. The first part of the experiment was this odorant natural stimuli given to the student. In the second, they observed a movie in which the actor of Marseille theater showed disgusting expression, pleasure, or neutral expression. Well, the result of the experiment is here. First of all, look at the horizontal section B. In horizontal section B, it's very clear that there is activation of the rostral insula. It's not original finding because at the beginning of the century, a similar thing has been described in London. So the anterior insula is activated by rotten eggs. That's the best stimulus. Every subject is disgusted by rotten eggs. But the most important finding is the following. When we look at somebody who is disgusted, we have an activation of the same voxel. The white voxel are voxels that are activated both when you have odorants, disgusting odorants in your nose, or when you see a person who is disgusted. The same voxels, it means the same population of neurons. What it means, that you and I are disgusted in the same place. The same neuron fire when I am disgusted and when you are disgusted. It means that that's empathy, the basis of empathy. But empathy, I don't claim that empathy is something related to be good, to be bad, and so on. But empathy for me is when you and I are the same state. And that's a typical example in which the same neuron fire when I am disgusted and when you are disgusted. Now, these are some data, but there are other data in favor of this. For example, if you stimulate, also in human, that has been done in Lyon, if you stimulate this area, the person is disgusted and sometimes is even vomiting. So it's a general thing. Furthermore, I have no time to speak about the whole literature, but there are data on lesion of bilateral lesion made in London first, and then also by adults and the other. What happens when a person has a bilateral lesion of the insula? That he doesn't recognize disgust anymore. One example, I think, was adults show it vomiting and asked, what do you think about this food? And the guy said, delicious. So he has no idea, although conceptually he can say what means disgusting is something which is unpleasant, which people doesn't like, and so on. So it's a clear distinction between what you act on something and what you... So I think that's a fundamental distinction, that we can understand emotion of others by an empathic process, because what you feel, I feel. That's what happens. If I go outside and see somebody which has been killed by somebody, I will be tremendously emotionally involved. If I read that somebody died in Libya, well, it's a pity, but if you measure my blood pressure, I don't think it changed at all. So we have completely two different ways in understanding action. One is empathic, phenomenological. You and I are in the same state. The other is cognitive, rational, and so on. It's the same thing. Of course, what happens later, it's very complicated, because when I am in the same state as you, we are both empathic, it's maybe that I subsequently will add very nicely but I also be very nasty. If you are my enemy, I can kill you. So Dessetti did the experiment in Chicago on sadistic people, and they understand emotion very well. They have no problem in entering in the state of the other. So one should clearly distinguish the capacity to understand the emotion of the other in an empathic way and to decide what to do later, compassion or no compassion. It's very complicated. But I want to finish with something else, with the limits of brain imaging. Many of experiments which I showed to you are brain imaging. But if you think there is so weak point with brain imaging, I think three are the most important. First, the conditions are not etiological. The person has to be still, cannot move, you cannot study movement, and if somebody moves, you stop because there is artifact. The second, the data are merely correlative. When you see that some area is active in fMRI, you cannot conclude that this area mediates, for example, pain. That's, I think, the typical error which has been done by many researchers to decide that the pain is there because you have an activation in fMRI during pain. Maybe, but maybe not, because pain is accompanied by many other phenomena. The third, there is no time. Our life, it's in time. What we got from fMRI? A picture, a static picture. But static picture doesn't mean we don't know anything about time. So, there is a way to overcome that, yes, although with many difficulties, but if you record stereo AG from a patient, you can, and you have a surgeon helpful, you can have a possibility to have data which overcome this difficulty. We collaborate since 4 or 5 years with a group in Milano, in Niguarda. They are surgeons of epilepsy, and in order to localize the epileptic focus, they do a series of experiments first. The group where you see here, we have the surgeon is Lorusso, the neurologist is Ivana Sartori, and the other group are researchers. So the experiment is rather complicated to do well. First, because you have to be sure that the patient is in a good condition beside epilepsy. So they do a structural MRI in order to be sure that there are no strange degeneration or tumor or something like that. They do a series of neurological and psychological testing, of course. Then they made angiography. It's strange because it's in blue, but that's the vessel. So angiography is important to have because the electrode will be introduced between the different vessels. And then they put all these electrodes, you see here, the red dots are the electrodes. So we have here 16 electrodes, and each electrode of this type that now with Bonini we are using also in the monkey, with, which you can record not only from the tip, but also from the shaft. So if you have 16 electrodes, with 10 points of recording, you have 160 points from one person. If you have a very active group, as that in Milano, you can have many patients. Because the weak point of this technology is that you can have only 4 or 5 patients and write a paper claiming, I don't know, that there is a gambling area, something of this kind. Well, so what we can do? The first thing is to stimulate and to see what happens. Here it's one very simple experiment. It's a clinical experiment, essentially. They stimulate the median nerve and look which area is active. And look at the number, because here the crucial point to be sure that what I'm saying or the researchers are saying is the number of points is high. Here we have 11,000 cortical leads, so a lot of things. In order to understand well the technique, you have to use flat maps. Flat maps is here. Why flat maps? Because gray matter is essentially in the solcy. So you have to open and to see. So in this case, it's written, you probably don't see, but anyway, area 4 is in the center, rostral pole is there, occipital is there. Now, let's imagine that I have no time. I stimulate the median nerve, no time. Look at all the activation I have. Here is the result. I have something yellow, so very strong in corresponding area 1, 2, and then a big red spot in the brain. Now, let's see what happens in time. What happens after 10 milliseconds? You have the classical S1 area that you see in physiological textbook, but after 40 milliseconds, already the motor system is much more involved than S1. And it's interesting that after 120 milliseconds, a lot of time, you have a strong activity in the region, in the perisylvian region. So stupid stimulus, like a stimulation of a nerve, actually, it's encoded in the brain for a long time. For which purpose, I don't know, maybe for memory, for remembering. If you think about the experiment of Ranulfo Romo, which examined how we keep in memory a stimulus, probably for that. But you see the big difference. It's not only S1, a simple stimulus, like stimulation of median nerve determines all this. But the result is even more interesting if you have intracranial stimulation. Here you see the cingulate. The subdivision of the area is done essentially according both Focht and Gallagher-Palomero, Zille's group. In traditional terms, the rostral part is area 24, the posterior is 23. Now, look what has been attributed to anterior MCC. Feedback processing, pain, salience, action-reward association, conflict monitoring. I have not put the name of the author, but these are famous scientists. It's not some young student courageous. For example, Michael Poser, which I think one of the greatest psychologists of last century, put in the Stroop effect, the activity of this area, saying this area is important for Stroop effect. Maybe, but it's not crucial. Now, let's forget about that and see what happens when we stimulate this area. And I will show you first the data following stimulation of what is called with the antero in blue, the medial part, which is still area 24. Now, it's similar to what we did in the monkey. It's a stimulation of this area.
1, 2, 3, 4, 5, 6.
C'è. Cosa è successo?
Che vuole andare via?
I want to go away, he said.
Che vuole andare via?
And we can repeat that many, many times. So this area, it's nothing to do with higher functions. Why should be higher function located in cingulate, which is a very primitive area? Rather, it's an area which probably prepare for action, give you a kind of stress or something of this kind. Here, it's another thing. In this case, it's against me, because a single neuron experiment made by a surgeon, by Hutchinson, who demonstrated a mirror for pain in cingulate. In one part of the experiment, he pinched himself, and in the other, he pinched the patient. Well, he concluded that's for pain, but he was so intelligent that he stimulated this area, and there was no pain. So he said, mysteriously, we have neurons which respond to pain, but there is no pain in this area. Why? Because it was no pain. It's a correlate of pain. When you are in pain, you have also increase in it's a kind of stressful stimulus. There is a nice experiment with stimuli which are unpleasant, which determine activation of this area. I will conclude with the stimulation of another area, so that's point which I indicated now. It's how dangerous it's made correlation with fMRI. You correlate something, you publish a paper, you said, I localized pain. Is it the anterior part of cingulate in area 24? Wrong. This area is not for pain. It indicates some activity related to the pain, but it's not pain perception. Now, the last thing is what happens when we stimulate the PACC, the rostral part of the insula. Look that we do the experiment, or stimulate all the areas, not in one subject, one area, another. Now, the stimulation of a PAC. This girl should be operated. certainly is not in good mood, he is in the ward, and now we stimulate.
Se lavoro coltello, maestra, ferro, gatto, arancia, pulsante alto. Un attimo di...
She's laughing. And here is another subject, same area, same stimulation. Now we have many, we published at the beginning with few, but now we have many of these experiments.
Allora, mi dice il suo nome e cognome, data di nascita. Cosa ride?
He cannot stop. And here is another case that is interesting because he says something.
Zanzara, foglio, pane, schermo, borsa, albero, nuvola, cancello, laccio, acqua. Zanzara, foglio, pane, schermo, borsa, albero, nuvola, cancello, laccio, acqua. Mi viene fuori così, non sono io.
He says, it comes from me. It's not me. I am laughing, but it's not me. It's extremely interesting. Well, to conclude, I started with mirror. I will finish with mirror because we have an idea. Fausto Caruana was the guy who did it. What happens if we, recording from the same point which determined laughing, present a movie with laughing? And what happens? It's here. So look at the red line. That's the high frequency EEG. It's the gamma, which is activated when the patient sees somebody laughing. So my laughing center became active when you see somebody laughing. So it's the same model which we proposed for the motor system. Thank you.